Hi, champs. Welcome back again to all of you in the another Sunday live session. And we have a very special guest with us today, Jasmine Florentine, who's a mechanical design engineer, author, and also the teacher. And today she will be delving into the fascinating world of paper engineering and how it can be used for telling a story. And along the way, if you have any question, you can ask your question in the live chat without any hesitation. Thank you so much, Jasmine, for joining us. And over to you.
Thank you. So I will get started then. Thank you for the nice introduction. I've got presentation as well, and I'll show a couple live examples. So just a little bit more about myself. As was already mentioned, so I studied mechanical engineering at MIT, where I focused on product design. But I've always really loved art and storytelling. And so I really try to combine all of those things, engineering, art, and storytelling. I am currently a freelancer. So I do everything from mechanical design engineering, as well as STEM content creation, so more on the education side. And I also write and illustrate STEM themed books for kids. So before I went freelance, I worked for First Robotics. And so they're a nonprofit that runs robotics competitions to get students interested in STEM. So these were some of the games that I worked on, and I was an engineer helping design the field. So as you can see, there's a lot of mechanical engineering that went into it, but I also sort of brought in my artistic side because all the games had a theme. So that was a really cool job. And I highly recommend checking out First if you haven't. The only reason I left the job is because I left the US. And so when I did that, I switched to freelance. And as a freelancer, as I've mentioned, I've done all kinds of stuff. I also wrote a book that is sort of like it's a fantasy adventure book, but with a STEM theme. So the characters build projects to get out of different scrapes. And then the end of the book has instructions on how to build all the projects. It's called Hexallen and the Clanksmiths, and this one's already out. And I'm currently working on a comic book called The Adventures of Maker Girl and Professor Smarts. And I can't say too much more about it, but also it has a STEM theme to it. So I've also done a bunch of other stuff sort of in that education and storytelling space as a freelancer, like helping write a STEM game, helping design curriculums and lessons. And then one of the other things that I started doing was during COVID lockdown, I started building paper robots. And I started doing this specifically because I wanted to explore how, with sort of a very basic kit of electronics, you can build robots without needing access to a 3D printer or a laser cutter or machine shop. Because, first of all, a lot of people don't have access to those. I don't have access to those till very recently. And also, it was lockdown. Like, I had basically paper and the things around the house. Funny enough, I used to do origami as a kid, so it actually worked out very well using these origami skills again. So for me, paper engineering, because I'm a mechanical engineer, I love making things move. And specifically with those movements, telling stories. So there's lots of different ways to make things move. These are supposed to be GIFs that move, which apparently they are not showing up that way. So I'm sorry about that. If you want to see the actual moving image, there's a link to my website at the end. Yeah, sorry, it won't be quite as exciting without the movements. But anyway, so in terms of making things move, I've done things without any electronics at all, just like wind power. There's also ways to do things cranking it by hand. But the thing that I most love exploring is physical computing, which is basically robots. So just to give a definition of physical computing for anyone not familiar, I just stole the definition from Wikipedia. Physical computing involves interactive systems that can sense and respond to the world around them. And so the sense and respond part is the really key thing there. So sense and response relates to inputs and outputs. And so senses or inputs, inputs are basically what a computer gets from the world around it. It's the way that a computer senses things. So it has a number of sensors that can get in information like movement, touch, sound, light, buttons, and so on. And then it can respond to that, which is an output. And the output is the way that the computer can interact with the world around it. So lights, sound, if we think about traditional robotics, it's often movement. And so keep this definition of inputs and outputs in mind because it relates to the story element. So for physical computing, these are the tools I'm generally using, the microbit and the circuit playground, which are both microcontrollers designed for education. So, if you're already working with a bunch of things like Arduino, Raspberry Pi, microcontrollers like that, all this stuff still applies. It's just these are the ones I happen to be working with because I'm working mostly in the education space. And the nice thing about them, if you haven't tried them, is they already have a lot of built-in functions, which means you don't necessarily need to go and attach breadboards and circuits and sensors and things like that. And then to make things move, I'm mostly working with servos, which are basically very small motors with the gearing already built in. And of course, I'm working with paper. So let's talk about stories a little bit here. I mentioned that for me, what I love doing with paper engineering is telling stories. And I'm going to define stories very broadly. Like a story can be something like, obviously, like the book I wrote, or a comic book, or an animation. But I would also argue that a game can be a story, or a character can basically tell a very short story in itself. So for instance, whoops, I'm going to unplug this for a second. I would say that, here, I don't know if this can be seen now with the presentation. I'll remove the presentation from the stage for a bit. So this is basically a paper box with some motors in it. And the story I'm going to tell is actually, this isn't just a paper box with some motors. This is actually a robot named Ticklebot. And Ticklebot, when I plug him in, has very sensitive feet and is ticklish when I tickle his feet. Sorry, it's coming out a little blurry there. And so basically by giving this paper box an expression, some limbs, arms, legs, and most importantly, giving it sort of an input and output, a way that it's reacting to the world, I've told a story here about this paper box actually being a robot named Ticklebot. So that is, let me go back to this presentation. Oop. Sorry, I don't actually know how to go back to the presentation. Thank you. So I'm going to focus mainly when I say stories for at least the paper engineering part of this, I'm going to focus mainly on these really short character-based stories. So for an example, let's say there's a prompt of make a pet. So this is sort of the thought process that I would sometimes go through with when I'm trying to design a new robot. I like to think of the relationship of the inputs and outputs of physical computing, as we mentioned, like sensor, computer, outputs, and how that relates to animal or human senses. Because part of the story that we're trying to tell is that this isn't just a collection of electronics, but this is sort of like an animal or a creature. And so you can think of the inputs relating to animal senses, such as sight or hearing or touch. The computer is sort of the brain, and then the output is basically like a muscle. And so the question is, how can you use these inputs to think about what senses does your pet have, and then how does that translate to their personality in this story you're trying to tell? So for instance, again, I'm using the microbit and circuit playground, but this applies to other microcontrollers. They have touch sensors built into them, and the touch can be used directly, or you can attach something like aluminum foil or conductive tape. And again, I'm really sorry that these aren't moving. If they were moving, you would see that when you pet the dragon there, it reacts by wagging its tail. The scorpion, when you touch the tip of its tail, reacts by pulling its tail in. And the ticklebot, as you saw, gets tickled. And so these are all different ways with touch to interact with your robot. So sound is another one. They have built-in microphones. And so once again, you can think of the different ways that your pet can interact with sound. So again, when you snap at the Octobot, it pulls in all its tentacles and it reacts to the sound in a way that startles it. And the other one, which again, I'm sorry, it's not working, is one that when you play sound, it cheers. So these are just different ways that show that these robots have different personalities. One of them doesn't like sound and is startled by it. The other one likes sound and is excited by it. And I have a live example. So fortunately, that one will move once I turn it on. So this guy reacts to sound by moving with me, so it can sing along. If I, sing do 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 mana mana. So that's another example of using sound. So if we go back to the presentation, movement is another great one. They have built-in accelerometers. I don't actually have an example, but you can imagine that you have a pet that likes to be picked up, or maybe it doesn't like to be picked up, or it likes to be shaken. Conductive connection, that's just closing a circuit. So for both of these, when you give them an object, it closes a circuit and they both react to it. Proximity. So actually the microbit does not have a proximity sensor, but it has a light sensor, which can sort of act like a proximity sensor, because if you get your hand close enough to block the light, it sort of is looking at distance, or you can actually just attach a proximity sensor. So in this example, when you move your hand close enough to the butterfly, the microbit senses that, and the butterfly reacts by fluttering its wings. And so that's just a couple of examples of the way you can use different inputs and relate them to how you tell this story of what is this creature. There's obviously other inputs you can work with as well. There's buttons, magnetic sensors, temperature, you name it. So what about the outputs? We've talked about the creature gets an input and that is something that it's going to react to. So the question is, how is it reacting? And what personality does it have, which will in turn affect its reaction? So we look back at these two again. At the end of the day, they're both basically the same thing from a technical perspective. They're both elaborate paper boxes. They're both responding to the same input, which is touch. They both have conductive tape or aluminum foil that when you touch it, that is used as an input. And they both have the same output, which is movement. But I've told two totally different stories here. So the one on the left is an angry scorpion that doesn't like to be touched. And the way I've told this story is, first of all, by its reaction. So when you touch it, it reacts by pulling away from you, by curling up its tail. And I've also told this story just with its expression. You look at it and it looks angry, like it doesn't want to be touched. Whereas on the right, again, same thing. It's just a paper box that you touch and it moves, but it's a very different story. The story here is of a dragon that likes to be pet. It reacts by wagging its tail, which is a happy movement, and I've drawn a smile on it. So with the outputs, you can think about what is the personality of this creature like. And so again, just quickly, you can use movement by attaching servos or motors. And there's other outputs you can explore as well. So you can use light For instance, the Microbit actually has on their website a virtual pet that reacts in different ways. Like if you move it or shake it, it has a facial expression and sound. So you can have a pet that reacts with sound by chirping happily or maybe growling angrily. So I've talked a lot about the inputs and outputs, and that's sort of the electronics engineering side of paper engineering. The other side of it is the mechanical side of it. So how do you actually make things move? And as a mechanical engineer, I love thinking about this. And what I love doing is taking traditional mechanical movements like pulleys and gears and all of those sorts of things and figuring out how I can translate it into paper, cardboard, and just other materials around the house. So I'm going to go through sort of a number of mechanisms that I've worked with. But again, the possibilities are infinite. This is just some of the stuff I've explored. And I highly encourage you to just take a bunch of materials and just experiment yourself. Again, I've included a bunch of resources at the end. So I'm sorry again that the images aren't moving, but if you want to look at it afterwards, they're all on my website. So direct drive is just basically when you attach something directly to the servo itself, like I did with the Ticklebot is, whoops, this is just the servo arm and the arm attaches directly to it. So, there's not really a mechanism there. Same with the butterfly. It's just the wings are attached directly. Gears. I love gears. I think it's a mechanical engineering thing. So on the left, those are laser cut gears through PaperMech, which is a website that has a bunch of really cool free mechanisms like gears and cams that you can cut on a laser cutter. I don't actually have access to a laser cutter. Somebody sent me these. So I also played around with making gears from materials at home using just wooden dowels and cardboard. And so on the left, those are actually wind-powered gears made out of cardboard. And on the right, those are more of the PaperMech gears, just in a different configuration that causes it to spin as opposed to go up and down. String. String is so much potential to do so many different cool things. So the one on the left works as sort of a rotating drum that pulls a string up when it wraps around it. So you can have something that lifts and closes. And then on the right, there's that straw on the motor acts as a pulley basically and pulls in 8 strings, which pulls in all 8 tentacles at the same time. Lots of other things you can do with strings. So the way the scorpion tail works is actually just there's a piece of string that goes the length of the tail and it attaches to the end of the servo arm. When the servo arm angles forward, it pulls the string and that causes the tail to curl in. And the rabbit there, same idea. It's got a servo on the inside, and when the arm goes down, it pulls the string down, which pulls the ears up and down. So the ears go like that. Cranks and linkages. So on the left is a wind-powered frog. That is the same frog that was on the bicycle on the wind-powered side. And that's just using a crank mechanism. And then on the right is a T-Rex that basically walks using a linkage system just made out of cardboard and like wooden dowels and things like that. Belt drive. I know this looks like gears. I actually cheated. These are not functioning gears. What's actually driving this is one servo on the inside that's attached to wooden rods using rubber bands that work as a drive system, which, by the way, I don't actually recommend doing because the rubber bands stretch over time and then kind of like lose their tension. But it was something I was experimenting with at the time with the materials I had around the house. So the list just kind of goes on. And again, you can look on, there's a website called 507 Mechanical Movements for inspiration. All of the robots that I've shown in the slideshow here, they're all on my website, and there's instructions for almost all of them. Some of them I don't have instructions for, unfortunately, but there's photos so you can try and recreate it yourself. And other examples, other resources that I wanted to highlight just for other amazing paper engineering makers and just tutorials and things like that. So first link there is my website, which again has all those robots and you can actually see them move. Paper Mech, which I mentioned before, they have a bunch of files that you can download to make paper gears, cardboard gears, and other mechanisms, and it shows you how to assemble them. When I do paper engineering, I'm mostly focused on movement, but that's not the only flavor of paper engineering out there. So Chibitronics combines LEDs and circuits with paper to do all kinds of paper engineering. Brown Dog Gadgets has a bunch of tutorials on their website, both for sort of like origami-based paper engineering, as well as sort of like Chibitronics LED-based stuff. Bird Brain Technologies mostly works with cardboard, and they have some tutorials on different mechanisms you can build just using things like cardboard, toilet paper rolls, string. Dazzling Discoveries is paper engineering without any electronics at all. It's just pure paper. So making things like marble roller coasters and mazes and stuff like that. Rob Ives has this incredible website with all kinds of automata. So that was something I didn't really touch on. Automata are when you make things move by human power. So, you know, if you have something where you crank it, that is an automata. So it's not a robot because it's not like I mentioned with physical computing, it has an input and an output. And so it reacts by itself based on the input. So like when I tickle the robot, it waves its hands without me having to do anything other than tickle it. So automata is human powered. And so it can do, it can't react to something by itself, but you can do a lot of really cool movements. And he's got a lot of templates on his website to build really amazing things. Again, using paper and just materials around the house. Cecilia Hillway is another person who does amazing things combining art and technology and makes paper robots. And then the last one was 507 Mechanical Movements, which, like I said, sometimes I like looking at for inspiration on, okay, how can I take this and then make it into a mechanical movement? So yeah, I thought I'd leave some time for questions at the end.
Yeah, thank you, Jasmine, for such an engaging and interactive session.
Thank you. Yeah, I'm sorry that the videos don't move. If there's, I don't know if there's a way to show it. Oh, I can do share screen actually if there aren't questions and show. I'm sorry, I didn't realize that earlier, and show some of these things moving. If there's interest.
Okay, so I have a
Oh yeah.
question. So the first project was Tickleboard, I think, which you posted on internet.
The first project, what?
Tickleboard.
Oh yeah.
So from where you got the idea?
Oh, that's a good question. Yeah, so it actually started with I was talking to another maker who Jervon Moss, who makes really cool companion robots, and they're these amazing like 3D printed robots that look like different animals like spiders or monkeys, and they like sit on your shoulder. And I was like, these are so cool, kids would love them, but most kids like don't necessarily have access to a 3D printer. How can we make something that a kid could actually build? And he was like, well, I don't know, maybe, you know, cardboard or paper. So I decided on my own to start exploring that. I started with cardboard and found that for like smaller objects, I actually found cardboard more difficult to manipulate. And so I started with paper and just built this little rectangular robot. And like I said, I sort of thought about it through inputs and outputs of like, okay, what inputs and outputs do I have to work with? I want my output to be movement. What do I have to work with as an input? You know, I've got sound and touch and all these other things, and decided I wanted to go with touch. And so that sort of helped define the story of, okay, I'm going to touch this robot and it's going to react. What is it actually going to do? Wouldn't it be funny if I tickled it and it reacted to that? And so that's how that idea came about. That was a very long explanation, but yeah.
And one more, you shared 3 parts: input, mechanism, and output. So what is the most difficult part while making these type of robots or with the help of paper?
Ooh, good question. I think the most difficult part, two things. One is usually figuring out the mechanism. Like, you're seeing all these completed works, but most of the time I have to go through a bunch of iterations before I figure it out, especially if it's a mechanism I haven't tried before. So, like, I think I'm trying to think of an example. Yeah, so like the first time I did Octobot, I didn't start by just building the whole thing in one go. I started by trying to figure out what is this mechanism for the tentacle. So I just started by making one tentacle, putting a piece of string through, figuring out how I was going to wind it. And so usually there's just some trial and error there of figuring out, like, how is this actually going to work? But the other difficult thing is I really want to make these projects simple enough that, like, anybody can just print them out and make them. And so the other challenge is just designing it in a way that is simple. And so some of the things that, for instance, I don't have instructions for is because I never got around to sort of iterating it to make it simple enough for anybody to just pick up and build. So for instance, like the T-Rex there was fun for me to make, but it's not very easy to recreate. It was a bit like messy and kind of held together with a lot of hot glue. And so the difficulty there is if I wanted to make it something that anyone could build, I would definitely have to work on that mechanism some more to make it not just working, but something that is easy to make. And also, just, I want to give credit where credit is due. The T-Rex there, the design of the paper part was actually taken from Rob Ives has a T-Rex. And so I modified his model to work with mine. So again, check out his website. Lots of cool stuff.
Yeah. So thank you so much once again for such an engaging and interactive session. And your insight into paper engineering and storytelling were truly enlightening. And we appreciate your time, knowledge, and the enthusiasm you brought to our community. Thank you so much.
Thank you. It was really nice talking. Were there any other questions, or is that everything?
No, thank you.
Okay. If you want, I can show, just because we have 3 minutes, I can show you some of the moving stuff. Otherwise, again, you can just check it out.
Sure.
Yeah, okay. Let me just do that real quick. Share screen. Let's see if this actually works now. Are these moving?
Yes.
Yay! Okay. So just real quick is basically what I was trying to show is the different robots that are actually moving. And then I'll skip to the mechanisms because I think that's sort of the most fun part of it. So we have the direct drive, which is just attaching directly to the servos. Gears, so that's a rack and pinion on the left, which translates rotational to up and down. These are more standard gears, which are just taking different kinds of rotational movement. This is the string, so it wasn't really obvious there, but you can see now it's lifting the paper clips up and down. And this is pulling those tentacles in. Here's the scorpion. So what it's doing is the servo's pulling the string in, which moves the tail, and the ears there kind of bounce up and down just from a string getting pulled. I also did put a little bit of plastic on the back of the ears to give them a little more springiness because paper inherently is not very springy. And the plastic, I think I just took a packaging from something and cut it up and put it there. I save boxes and packaging and stuff and reuse it all. Here's the frog. You can see that crank linkage, and then there's the dinosaur walking by, and then there's this belt drive here. So yeah, I just wanted to show those. And then the one last thing is I mentioned, like, those two where it's two different stories, and you can see the way they're moving is very different. So that's all.
Good to see.
Cool. Thank you again so much.
Yeah, thank you. Bye.
Bye.